So very happy to be here. I'm Georgios Balikas. Currently, I'm a lead data scientist and I'm working at Salesforce Search, trying to improve the performance of the search engine there. In general, I'm very passionate about information retrieval, natural language processing, and machine learning. I really enjoy projects that are in the intersection of these fields. Currently, I'm trying to balance between career, family. I have two sons, and sports. I live in Grenoble, France, and it's just below the Alps. Now it starts snowing, and I'm very excited about this too. I'm trying to learn ski. I'm playing some tennis. I love cycling. I also love wine and cheese. And if you want to reach out, you can reach out in Twitter. You can reach out in LinkedIn or even GitHub. And as a matter of fact, I will be presenting about an open source GitHub project I've been working on in the last few months right now. So, what's the talk? What's the story behind this talk in particular? Well, I wanted to try sentence transformers. It's like BERT style models, transformers models that have been beating the state of the art in several tasks during the last few years. Sentence transformers is a Python package that lets you use such models. But how do we put such a model in production? Well, it's not that easy, and the most of these models they work on top of PyTorch. Usually in production setting, at least in our case, we want to serve such a model with TensorFlow. So it's the first obstacle. We want to have a single graph so that you have a query, you hit the graph with a query and you get predictions. Well, it's not really how these models work. You have a tokenizer and then you query the model. So this, along with other challenges in the process, inspired me to write this open source framework that is called TensorFlow Exporter, and it's currently available at GitHub. I will be sharing the URL shortly after. To the outline of my talk, now I hope I have convinced you that there is something for you to attend it. So I will start explaining a bit more the problem, and then I will deep dive in the sentence transformer package architecture. Hopefully, a solution will arise, and this will bring us naturally to the TensorFlow exporter package that I've been working on. So let's start with the problem statement. This is what you would do in a Python notebook environment if you wanted to use the sentence transformers library. You would first pip install it, and then you would import the sentence transformer class. You would define a model name, sentence transformers, all mini LM L6 V2 in this case. You will initialize the class, and well, you can get embeddings just by calling encode. You can hit encode with a single string. PyData is awesome, like I'm doing here, or even with a batch of strings, and you would get embeddings. These embeddings, at this case, is like vectors of floats of dimension 368 for this particular model, and you can use them in a downstream task. You can do information retrieval, you can do classification, natural language inference. There are several tasks where these models perform quite well. Once you have the embeddings, of course. So you have the model, you get a string, you get embeddings, and you continue on your pipeline. But what exactly is happening behind the scenes of this model.encode method, where a lot of things are happening in particular? And this is a screenshot taken from the Huggingface Hub model card of this particular model. We see that there is a tokenizer that is initialized, there is a model that is initialized, and then we start the process by querying using the tokenizer. The tokenizer itself does several things. Not only does it give us the tokens, but it also does padding, it also does truncation. So a lot of goodies packed in there. Once the input is tokenized, again, this can be either a single string or a batch, then you query the model. And this is not it. Then you need to know a few things about the model, and here in this case, the model does min pooling on top of the model outputs, and then there is also a normalization step. This is not the case for every model in sentence transformers. Different sentence transformer models require different steps after this model output step. So we need a way that can scale. And all these right now are happening mostly with PyTorch code, and PyTorch, you can perhaps see this F here with PyTorch token weights for the models. So there is a discrepancy between PyTorch and TensorFlow. Now, the question that naturally arises, and what I'm trying to answer in this presentation, is that can we bring some of these goodies in the TensorFlow world? In particular, can we have a single graph that does all of the steps that the previous slide showed? Tokenization, query the model, and perhaps post-processing of the model predictions. If we had a single graph that can do this, it would be easier to maintain and perhaps a lot easier to put such a single artifact in production instead of having several things, several moving pieces, just one graph. If we could do it, if we had a single graph, then it would be language independent. Then we're not really tied in Python anymore. Java and JVM in particular can read TensorFlow models, and it's easier if you have, let's say, a monolith that is written in one of these Java, JVM languages to integrate with it. So it's a nice thing if we can do it. And there is a lot of infra for serving TensorFlow now. Of course, Python is catching up, but things are moving slower in the industry. So perhaps one can use this infra to serve a TensorFlow model, a model that is written in Python, like most of the senders transformer models. It's not a trivial problem. Like trying myself to find a solution, I found several GitHub issues that motivate me further to deep dive and understand what is happening behind the scenes. And it's also a fun exercise. I really enjoy Sendes transformers and Huggingface transformers in particular. They work very well tied together, and it's a fun exercise, like to dig in and try to understand how these frameworks, what's their architecture, how do they work, and how you can build on top of that. And that was the motivation, the problem. We have a torch model, which is like a sequence of a tokenizer, a model, and perhaps other layers. And we want to be able to have a single TensorFlow graph. How can we come up with a solution? Well, before coming up with a solution, we need really to understand a bit more about the magic. So what is happening when one initializes a Sendes transformer class with a model name? Well, Sendes transformers tries to see if this is a local path or is just a model name that the model lives in Huggingface hub. Let's take, for instance, the case where it lives in Huggingface hub, then it automatically tries to bring this model on your local environment. And this model is cast on a particular path that you can, of course, change if you want to, but by default, it's cast on the torch cast path on your local machine. And it's not only a single file that is brought in your local machine, but it's several files like those that you see in the left part of my slide in this case. Now, as you can see, these are a mix of JSON file. JSON pertains to configuration. Probably you've done it in your life too. And there is also binary files titled PyTorch model bin. These are model weights. There are also text files, vocabulary.txt. So this, for those of you that have worked on, it means like mostly tokenizer configuration so that we can tokenize the input. Now, if we're looking for a single source of truth to make sense out of this, there is one particular file which is called modules.json, and its contents are shown on the right part of my slide, and it's a list of dictionaries. It's a list of dictionaries in particular. Now, module.json describes the exact architecture of each of the models. And here we're looking at the architecture not of all mini model, but of this model that's called the distributed BERT multilingual cased V1. And what we see is that this model is like essentially three things. First of all, there is a transformer part, and this is the first part. Then there is a second part, which is called pooling. And then there is a third part, which is called dense. What it really means is that you get the query, you first pass it via a transformer, you do pooling on top of the transformer outputs, and then there is another dense layer that further transforms the pooling outputs. Each one of these three models has a dictionary with like 4 key value pairs. What we care about here is, the order, the path. So here you see the path of the pooling is one pooling, And the type. The type is used by the library internally so that it initializes a transformer class type given the information that lives in this path, and the information here refers to config, vocab, and other files. When we have more elements in this sequence, like pooling and dense, we can see that we have these colored directories, and essentially you can see here one pooling is a directory in this path. Two dense is another directory on this path. And essentially each of these directories can contain configuration file, like the case with pooling. We only have a config.json file that describes how the pooling will be done. And then for the dense model, we have a config file and weights. For a dense model, the config contains the structure of the dense layer, input neurons, output neurons, and then the activation function also. And the binary file here contains the weights of the dense model in a torch format. As a summary here, we discussed that there is a modules JSON file that describes the architecture of the model, and then each module in this module JSON file can have one or more one directory associated with it, and each directory can contain one or more files that describes the usage of this module. And these are used internally by sentence transformers in order to initialize a particular class that is used as a part of a sequential model to get predictions out of it. Now, this at this point perhaps has already given you some ideas on how one can get this architecture, get this sentence transformer model, and translate it in a TensorFlow, in the TensorFlow graph, in the TensorFlow world. Essentially, the steps are shown in the slide, but first we need to read, understand, and parse this modules JSON file. Depending on the contents of this module JSON file, we need to implement each of these modules in a way that scales and extends with TensorFlow code. And then once we have all these modules, we'll define a sequential keras model perhaps that will be living on the TensorFlow world. So this brings everything together. And without further delays, let me start discussing a bit how I decided to implement this as part of the TensorFlow TF exporter package. Well, there's no surprise. After deep diving into the sentence architecture, the sentence transformers package architecture, I decided to implement exactly the steps that we saw in the previous slide in a way that scales and in a way that could be used to convert several models into a TensorFlow graph. Now, doing this is not exactly trivial. Like when you discuss the differences between TensorFlow and PyTorch, there are a lot of moving pieces, and people tend to implement things in their own special way. So there were at least two important resources that came to help to aid in this task. One was TensorFlow text. TensorFlow text is a package that it surrounds the TensorFlow world, and it's in this ecosystem, and it provides a lot of utilities that can be used for text post-processing and pre-processing tasks. So it makes it quite easy to work on tensors on the TensorFlow framework. And then, of course, there is Huggingface transformers, which is one of the packages that have really democratized transformers and BERT in the Python world. And this framework is written in a way that it can load and understand artifacts both from TensorFlow and from PyTorch. And oftentimes it makes it very easy to read a model and save it in a different framework. One of the most important and challenging tasks was how to convert the tokenizer and transformer model in a single graph. This was not trivial because the tokenizer does a lot of things essentially, and we had to maintain alignment between the sentence transformer dot tokenize method implementation with what we would write in the TensorFlow text world. So what is essentially a tokenizer? A tokenizer is a code that gets a string and tokenizes it based on a particular lookup table. A lookup table is a set of vocabulary tokens. These are subword tokens, and is used to split the text in tokens so that the model can transform them to embeddings. This can be implemented using TensorFlow text.BERT tokenizer method class. It already exists. It just needs correct initializations from information that already lives in this group of JSON and configuration files that I showed you that are cast by sentence transformer. So once you have text input or a batch of text, you just hit the tokenizer. The tokenizer is implemented with BERT tokenizer, and it gives you the tokens essentially. These BERT style models, they really need text that is up to a maximum length. So there is a round robin trimmer that can be used afterwards to ensure a maximum length. So let's say 512 tokens. And now the output of this part is a sequence, tensor essentially a sequence of tokens that all have a maximum length. We need the start and the end token. These are particular tokens that are used by these sentence transformer models. It's easy to add them with standard TensorFlow tensor operations, so I'm not describing the implementation right here. And then we need to do padding. Padding ensures that every tensor in the batch has the same dimensions. If some of them are shorter, then we pad them. And this is what padding does. There is a pad model inputs implementation within the TensorFlow text package, and this can be used. And at this point, we have exactly the tokenization output that sentence transformer tokenize generates. And at this point, we can hit TensorFlow auto model. It's called auto model here because, it can read Huggingface transformer models both from PyTorch or TensorFlow model weights. So it automatically decides, and it also automatically decides the architecture of the model. Now you hit the model with this output of the padding layer, and then at that point you get the model output embeddings. Of course, in the previous slide, I described that the story does not finish there. There is also pooling. There can be normalization. There can be dense layer on top of these outputs, but these are probably simpler to implement using TensorFlow and trying to get the Torch models to work with TensorFlow. I've been doing this in the package, but I didn't want to save. I wanted to save time and not go through more details on that. So this, as a result, we have TensorFlow Exporter, which is like a package that currently lives in GitHub. You can use it as shown in the excerpt on my screen. Python, convert to a single graph. You provide a model name. It expects a sentence transformer model, and it outputs on a directory of your choice a TensorFlow model. It automatically saves the assets, keras metadata, and the save model protobuffer and variables. So everything that you need in order to load the model from TensorFlow and query it. The process has been like we need to maintain some sanity. So part of the process was answering the question, how can we be sure that everything is aligned? So what essentially this is the testing strategy that TensorFlow Exporter and myself have been using throughout the process. We first start with a model, sentence transformer models. We have test queries. We issue these queries to the model and we get the predictions. Then everything is tied in a keras model using the process that I described in the previous slide. You have the keras process in memory, and you can query the model and get predictions. Of course, you use the same test queries. So these predictions needs to match with the sentence transformer model predictions. And then there is a last step, model persistence, where you keras.save the model, and then you tensorflow.load the model. Essentially, at that point, you have a graph, and you have a serving signature, and you can hit this graph with test queries, and again, you get tensors, get the output of the model. What we really want is for all these outputs to match, and this is like sanity checking and testing as it is done in the TensorFlow exporter model. I'd like to thank you. This model currently lives in GitHub. Issues and suggestions and PRs are very welcome. And feel free to reach out to me either at Twitter or at LinkedIn or at GitHub in every ways. I will be around in the conference. I'm attending this. I will be also on Discord. Thank you. Thank you very much.